Alright, in this video we'll be talking about internal resistance. Alright, to start off we can draw out a simple circuit right here with one resistor, like so. And so we can just use this circuit to remind ourselves about the energy changes that happens within a circuit, okay? Alright, so if we set this power supply to 5 volts, remember that the power supply is going to add 5 joules of energy per coulomb of charge that goes through that power supply. Okay, and as that charge flows through the resistor, each coulomb of charge is going to lose 5 joules of energy. Okay, all right, so in other words, our power supply provides 5 volts and our resistor uses 5 volts. Okay, so within this circuit, there are some assumptions that are being made. The first assumption is that our wires are ideal, meaning their resistance is 0. Okay, and same with the power supply. We're saying that the power supply has 0 resistance. However, in reality, neither of these statements are correct. In reality, wires do have some resistance, and also in reality, power supplies also have some resistance. Okay? And so because our power supply and our wires both have resistance, some of our energy is going to be lost. So what that means is, not only are we going to have energy being dissipated due to our resistor, but we're also going to have energy being dissipated throughout the circuit, okay? And so if you think about it, that's very, very hard to quantify. How do we know how much energy is being lost due to the internal resistance, okay? And so that's what we call the resistance from the power supply and the ideal wire. We call that an internal resistance, all right? So the way we quantify this concept is by modeling the internal resistance as its own resistor. Okay, so just like how this external resistor takes away energy from the circuit, we can model the energy being lost throughout the circuit through the wires and the power supply as its own resistor, right? And so what that will look like is if we have our power supply again, okay, and we have again our resistor right here, our internal resistance can be modeled right off our power supply in series, like so. And we can draw a little dotted box around this power supply to indicate that this is sort of a black box, meaning this isn't what's actually going on inside. More so, this is just a simplification of what is happening in reality, okay? And so now that we have this internal resistance, we can again assume that our power supply has 0 ohms of resistance, and also our ideal wires also have 0 ohms of resistance, okay? And again, this is all due to the fact that the resistance of the power supply and the resistance of the wires is being accommodated by this internal resistor, okay? And so we can denote this resistor as little r, okay, to denote the internal resistance of the circuit. So let's say our power supply provides 6 volts, okay? And our resistor, our external resistor, has 6 ohms of resistance, and let's say our internal resistor has a tiny amount of resistance, let's say 0.4 ohms, okay? And remember what this means is that the total resistance of our wires and our power supply add up to 0.4 ohms, okay? So firstly, we need to define something just to make things clearer. What we're gonna define is what's called the EMF, okay? And this stands for electromotive force, all right? Electromotive force. And so what this is the energy that is supplied by our source that drives current around the circuit, all right? Energy supplied by the source that drives current around the circuit. And in our case, that is going to be 6 volts, okay? So example being 6 volts. And what this is the total possible voltage that can be supplied by our source when no current is flowing. Now, why do we specify when no current is flowing? Is because when there's no current flowing, then effectively our internal resistance doesn't do anything. Now, again, as our internal resistor is modeled as just a resistor, even for our external resistors, when there is no current flowing, no energy is being taken away from the power supply by the resistor when no current is flowing, because the resistor can't take away energy because no charge is flowing through the resistor. Same thing for internal resistance. If no charges are flowing through the circuit, that means no energy is being lost due to the internal resistance. And so that's why when no current is flowing, the potential difference across the battery is equal to the maximum possible total voltage by the supply, okay? And so that leads us to the idea of terminal voltage, okay? If we again grab our circuit and we measure the voltage across the terminals of the battery with the internal resistance, okay? And so our terminal voltage is equal to our EMF minus our lost volts, okay? And our lost volts are due to the internal resistance, okay? And so we measure our terminal voltage again when current is flowing. okay? And so when current is flowing, and therefore energy can be lost as charges flow through the power supply and the wires, and therefore our internal resistance has a factor on the voltage that is measured across our terminals of our power supply, okay? Now, one thing to note about EMF is that EMF is constant. However, our terminal voltage is not constant. Our terminal voltage actually decreases over time. And the reason for this is because our power supply gains internal resistance over time. As you use the battery over and over and over again, it will degrade further and further and further, and therefore gain more internal resistance over time. And so our terminal voltage decreases over time due to an increase in internal resistance. Okay, all right, and so that's our intro to internal resistance. Okay, so let's move on to something over here. What we're gonna do is we're gonna look at a circuit, okay, and we're gonna look at an equation by applying Ohm's law to this circuit, which has an internal resistance, okay, like so. So we can label this 6 volts once more, this as little r, and our actual resistor as big R, okay? If we were to analyze the energy changes across this circuit, we know at the start we're going to gain 6 volts, and we know our 6 volts is our EMF, okay? And so we start off with our EMF, okay? And so as the current flows through, it obviously flows through this resistor, and the voltage drop due to this resistor is equal to the current that goes through this resistor multiplied by its resistance, okay? And we obviously denoted that this resistor has a resistance value of big R, okay? And so we get this equation right here. And so we can minus IR from our EMF. And so as the current continues, we're obviously going to be met with this internal resistance. Again, this resistor does not exist in reality. This is just a model, okay? And the voltage drop across this internal resistor is going to be the current that goes through it multiplied by its resistance, which we can denote as little r, as we've seen over here, okay? And so we can minus I little r, okay? And this all should equal to 0. All right, that is a direct application of Kirchhoff's voltage law, where the voltages in a closed loop should equal to 0, okay? All right, so again, this value right here is the potential difference supplied when no current is running. Then when current does start to flow, we're going to lose this potential difference to the actual resistor that's in the circuit, and then we're going to lose some voltage due to the internal resistance, okay? And that all equals to 0. And so what we can do is we can rearrange this equation slightly, and we get the EMF is equal to the voltage drop due to the resistor plus the voltage drop due to the internal resistance. And so if we were to measure the voltage across this power supply terminal, okay, it would have to be like so, okay? Now remember, we're not allowed to measure the voltage across the terminal like this, because that does not include our internal resistance, and therefore it does not accurately model what happens in real life. And so we must include the internal resistance and the power supply when we use a voltmeter, and so the voltmeter has to be on the outsides like that, okay? Has to start here and then end here, okay? Now I hope you can see that this voltage reading should be the exact same voltage reading that we would have across this resistor right here. Okay, we can see that this side of this voltmeter shares a node with this side of this voltmeter, and this side of this voltmeter shares a node with this side of that voltmeter, okay? And so therefore, their potential difference must be the same. We can also see this in this equation. If we imagine the voltage of this top voltmeter, it's going to be the EMF minus the internal resistance. And the voltage across this is purely going to be the voltage drop due to our resistor, okay? And so therefore we get EMF minus our internal resistance is equal to our resistance drop due to the resistor. And as you can see, our intuition is backed up by the equations, okay? And so because we know that this is the terminal voltage, which we can denote as TV, right? We can see that from our definition of terminal voltage right here, that this is the terminal voltage, okay? That means because the voltage across this single resistor is equal to this scenario right here, and this scenario is our terminal voltage, we can say that IR, which is the voltage across our resistor, is equal to the terminal voltage. And so therefore our EMF minus the voltage drop due to our internal resistance is equal to the terminal voltage. And so if I were to rearrange this equation, we would have our TV is equal to negative IR, which is our voltage drop due to our internal resistance, plus our EMF, okay? And so what I want to do with this equation is see if we can measure the EMF. Because even though when you buy a battery, it will say 6 volts or something on the battery packaging, and that value is our EMF, right? That is the maximum voltage that that battery can provide, okay? Even though it says 6 volts, we're not always going to be given the actual value. And so how do we calculate our EMF? Well, the way we would do that is by using a graph and inferring from that graph, okay? All right, and the reason why we have to do this method is because we can't actually measure our EMF. The minute we try to measure our EMF, we're putting a current through the circuit, and therefore that is no longer our EMF, because remember, our EMF is when no current is flowing, okay? So the way we would do that is to set up a circuit which has a variable resistor attached to it, okay? So we'll still have our internal resistance right here, but we would have our resistor here, and this is going to be a variable resistor, okay? Again, remember, a variable resistor is a resistor that can change resistive values, okay? So it can go from 3 ohms to 5 ohms to 7 ohms back to 2 ohms, you know, it can change its resistive value, okay? And again, we draw our box around our internal resistance and our power supply. And so let's chuck an amp meter into this circuit, and let's also measure the voltage across this resistor. Remember that this is equal to the terminal voltage, okay? All right, and remember, this is little r and this is big R, okay? And so what we want to do, collect values of our voltage. Remember, this is our terminal voltage and our current, okay? And remember, this is going to be the current measured by this amp meter for different values of R. Okay, and remember, this is big R, so it's different values of our variable resistor, okay? And so if we were to plot V versus our I, okay, so our voltage versus our current, remembering that our voltage is actually the terminal voltage, okay, remember? This is because this is this voltage right here, and that voltage is equal to the terminal voltage as we established up here, okay? And this I value is obviously the current throughout the circuit, okay? And so if we were to start off with a minimum value of our big R, okay, so a minimum value of our variable resistor, and so that means that this resistor is as low as a value as it can possibly be. We are obviously going to have the highest amount of current, okay, flowing through, okay, so this is the highest amount of current flowing through and the smallest voltage measured across, okay, so there's the smallest energy drop per coulomb of charge, because there's the smallest amount of resistance. And so therefore the charge can flow more freely, meaning the current is highest, okay? But then if we were to start increasing this R value, we would imagine that this resistance value is going to continuously get smaller and our voltage value is going to get larger and larger, okay? And it should follow sort of a straight line. Now that makes sense. Obviously, as our resistance value gets larger and larger, that means charge can flow less easily, meaning our current will decrease. But also because charge has a harder time getting through the resistor, there's obviously going to be a larger energy drop per coulomb of charge, and so our voltage is going to increase. If we set R to max, we're eventually going to get to a point where this resistance value is so large that practically no current can flow through the circuit, okay? So the resistance of the circuit is so big that no current can flow. And so what that's going to result in is a current of 0, okay? And so that's going to be our y-intercept, okay? Like so. Now, if we remember, our EMF is our voltage value when no current is flowing, okay? And so therefore, this value is our voltage value when no current is flowing. And so this y-intercept is our EMF, okay? And that's the y-intercept. There we go. Now, it's important to note that this value cannot actually be found to be exact. That's why I said earlier we need to infer from a graph, okay? Because we can't actually get the current value to be absolutely 0, we can only get it to approach 0. What we would do is form an equation for these plots, okay? And then backtrack to see where the y-intercept would be, okay? But it's important to note that that is an assumption, and we're assuming that the trend carries on, okay? And it's also important to note that this is a very strong assumption, okay? We can actually make this assumption and be fairly confident with the value, okay? So even though it's a sort of a guess, the guess is pretty accurate, okay? Now we can also see from this graph that as current increases, our terminal voltage decreases, okay? But we said over here that our EMF is equal to the voltage drop from our resistor right here, plus the voltage drop due to our internal resistance. However, if more current is flowing through the circuit, okay, let me redraw that equation. If more current is flowing through the circuit, okay, so we're at this side of the graph right now, we can see that our terminal voltage is getting smaller, okay? And so if this value is getting smaller, that means as more current is flowing through the circuit, our internal resistance is getting larger. And so therefore, if more current is flowing through the circuit, our internal resistance is going to be greater. So more volts are being lost due to the internal resistance, meaning more joules per coulomb of charge are being lost to the internal resistance. And that will be it for our part 1 of internal resistance.